Good afternoon, everyone. My name is Yao. Today, I'm going to briefly talk about the surface area and volume of a sphere. I will divide my speech into four parts. In the first part, I will introduce a bit about the spherical coordinate system. And in the second part, I will show you how I derive the formulas for the surface area and volume of a sphere. And in the third part, I will explain the relationship. And finally, I will talk about other dimensions. So from high school, we have already learned the formulas for the volume and surface area of a sphere. The volume is simply 4/3 pi r cubed, and the surface area is 4 pi r squared. It's obvious to see that the derivative of the volume with respect to r is the surface area. But how do we get these formulas? To derive them, I will introduce the spherical coordinate system first. In the spherical coordinates, we now have r, theta, phi, and they are related to the Cartesian coordinates x, y, z by the equations on the slide, and each of them have their own restriction. For instance, r is always greater than or equal to 0, theta is always between 0 and 2 pi, and phi is between 0 and pi. So to transform from one coordinate system into another, we need to find the Jacobian. And the Jacobian means the determinant of the Jacobian matrix. And as you can see on the slide, the final result we get is r squared times sine phi. As the Jacobian essentially tells us about how infinitesimal area or volume element transforms under the coordinate transformation, we can now derive the formulas for the area element and volume element in the spherical coordinates using the Jacobian we just found. I have included some diagrams and animation for you to better understand what a volume or area element looks like in the spherical coordinates. So the volume element looks like a slightly curved block hugging a sphere. And when it becomes infinitesimal, the curvature in the shape becomes negligible. So it can be treated as a rectangular box, and its volume is simply the product of its three side lengths. And the area element is simply the volume element divided by dr. And the results we get actually agree to what we found using the Jacobian from the last slide. So now it becomes easy for us to find the total surface area of a sphere with radius r. We simply integrate the area element over the entire surface of the sphere by using a double integrals, and the result we get is just what we expected. And similarly for the volume of a sphere, we use triple integrals that sums all volume elements inside the solid region. And again, the result we get is exactly what we expected. When I solve the triple integrals from the last slide, there's a reason why I integrate over r in the end. So we get this equation. Since we already know the formula for surface area is 4 pi r squared, it can be then written in this way. Now let's recall the definition of integration. An integral is a process of adding up small things. This integral can then be interpreted as that the volume of a sphere with radius r can be found by summing over infinitely many surface area, each with 4 pi r squared, multiplied by the incremental change in r or delta r from 0 to the radius. Now we come to the most interesting part. To make it more intuitive, let's think of a sphere as a series of concentric spherical shells added up together, like a type of candy called jawbreaker or an onion. And by the summation of the volume of each layer, we can actually have the volume of it. A small increase in the volume dV now is like adding a new shell or layer over the entire surface. As dr is everywhere constant and normal to the surface, it can then be regarded as the thickness of the shell, Hence, the volume added dV simply equals to area times thickness. And this also explains why the derivative or rate of change of the volume with respect to R is the surface area. So you are probably wondering whether the derivative relationship holds in other dimensions. And the answer is yes. Let's take a look at 2 dimension first. A sphere now becomes the circle, and we can still apply the idea. So the circle is made up of many concentric circular rings. Obviously, the derivative of the area is a parameter. But what about higher dimensions? The idea of viewing the sphere as made up of spherical shells can actually generalize into any dimensions. The volume of a hypersphere can always be found by an one-dimensional integral with respect to the radius r. And to further verify it, I have included some examples, so you can see that the derivative relationship also holds in higher dimensions. And this concludes my presentation. Thank you for your patience and time.
Okay, thank you, Yao. So has anybody got any comments, any thoughts, contributions? You've watched your peer do some work. What do you think? Any comments?
Hello, sir.
Yes, yes.
So I have